Hello everyone, here's another IB video. This time we're in the higher level and it's 9.1, simple harmonic motion. So imagine you've got a pendulum swinging back and forth. Here we go, this is red pendulum swinging back and forth. It's in simple harmonic motion, so we'll go ahead and assume there's no friction. This pendulum's just going to swing back and forth forever. Now imagine you're shining a light, here's the light, and you can see the shadow on this screen. If you were to match the motion of the pendulum to another metal sphere that's attached to a turntable, so you can see the shadow of this metal sphere on the turntable right here. If you were to match this pendulum swing to the exact period of the metal turntable, the metal sphere on the turntable, such that when the metal sphere was on this side of the turntable, it aligned with the maximum pendulum swing to this side of the pendulum, and vice versa on this side, you would see this this shadow here going back and forth, back and forth, back and forth, as the pendulum also went back and forth, back and forth. Now, this is kind of cool, because if you're watching from this side of the screen, there's your eyeball, you're looking at it from this side of the screen, this this ball going back and forth, it would be completely undistinguishable from, or indistinguishable from a spring, a horizontally aligned spring in horizontal motion with a mass. And we've seen this before in previous simple harmonic motion demonstrations. This is the idea we're going to be talking about, and the reason I wanted to show you this is because to get into the higher level stuff, we want to be thinking about simple harmonic motion being aligned with this circular motion. So think about how this simple harmonic motion, it can be thought of as circular motion. Okay, so we've made the connection to a circle. So let's go ahead and start labeling up our circle. I've already done the y and the x part of this, and hopefully it'll be no coincidence to you that this y part here is going to represent the y-axis on a graph in just a minute, and this is going to represent the x-axis on a graph. But again, what we're thinking about is this circular motion representing simple harmonic motion. So an object at a particular location on the circle is going to continue at a constant speed going round and round the circle, and the period of that is going to match the pendulum swing or the spring motion, exactly the same thing. So let's just make some labels here. I'm going to call this red arrow, I'm going to call it R, because that's going to be the radius of the circle. And of course we have an angle in here, let's call that theta. And what I want us to think about is the triangle representation. So I've got a right angle triangle here, and I will do it in green. I've got a right angle triangle piece here. So these two components of the triangle. So clearly using our SOHCAHTOA, we can say that this piece, this green piece here, we'll call this x, is the x component of the triangle. It's going to be, well, this is the adjacent edge of the triangle to the angle, so that's cosine, and the hypotenuse is r, so it's going to be r cosine theta. Okay, and then of course this guy over here is going to be y sine, r sine theta. Okay. The other thing to say is that, of course, now we're talking about circles, we're going to be thinking about radians rather than degrees, or at least we should be aware of the two different ways of communicating a change or an angle on the circle. But if we think about, and we've seen this before, omega is the angular frequency or the angular speed, and that's going to be equal to the change in the angle over time. Okay, the rate of change of the angle. In other words, if we were to do an entire circle, we would say that's 2 pi, right? 2 pi is an entire circle in terms of the circumference, and that would take a period. So 1 period would be the time with which it would take to go all the way around one circle, which is 2 pi, and that's the period. So we can start using these terms. In other words, I can rearrange this and say that the angle, the theta, is actually equivalent to omega t. So we're going to do some really cool things. We're going to do some substituting. We're going to play around with these equations because really the goal of this video is to show you where a lot of these equations come from. And then we'll talk about how we can use these equations to successfully solve some problems. But check this out. I've just said that the omega is, the theta is equal to omega t, the time. Now, if I make another expression for my x down here, if I was to imagine that my radius now is, let's go ahead and say that it's right here, right at this point here. That would be my maximum x value, correct? My maximum x value. So let's call that x naught. That's my maximum x value, which is going to be equal to r at that time point. And then that's going to be equal to cosine. And now rather than using omega, I'm going to say, rather than using theta, I'm going to say omega t. Okay, so I've just got a different way of writing that out. That hopefully makes some sense. We're going to use that in a minute. Equally, with my y, I can say that my y value, when it's at its maximum, which would be here, whatever time value that is to be at its maximum, I can make a statement about that by saying that y naught is equal to r at that time, and that's sine, and then rather than theta, omega t. Okay, so I've got these two statements. These are going to be important. We're going to use these, this one and this one. Okay, so now the fun starts. We're going to start thinking about how this circular motion, which is a simple harmonic motion, this motion round and round the circle, how we can map this onto some graphs. And we'll do a little bit of calculus, and we should get, our goal here is to be able to understand these formulas from our data sheet. We don't have to replicate this derivation, but it's important to see, and hopefully it gives you a bit of fundamental understanding. All right, let's begin. Now, I have chosen, completely arbitrarily, I've chosen to use x naught and minus x naught. Now, these are going to be my, obviously my maximum amplitude and my minimum amplitude. But I could have chosen my y naughts. It doesn't actually matter. It's completely arbitrary. I'm choosing x just because that's the language on our data sheet. You might see this in other forms where it uses a for amplitude and a naught for amplitude max. But we're going to go with x just to model what's on our data sheet. The other reason to do that is so that I can choose my x value to be minimum. Okay, so at the very beginning, and again, this is totally arbitrary, I could choose to have my beginning value as 0 or my beginning value to be absolutely max. It doesn't matter. I'm going to choose my minimum value, my starting position, to be 0. And the reason I want to do that is so that I can have a sine graph to start with, just because it feels right to start with a sine graph. So at time 0, our x amplitude is 0, because we're choosing that as our starting point. So there's my dot on my graph. As time goes on, this is going to increase. It's going to come up and then down like this. And there's my sine graph. So important things to note are the different parts of the graph, and we're going to think about the slope, because we're going to do some calculus on this. So the slope is important. This slope here is going to be my maximum positive slope. Slope at this point is going to be 0, hence the horizontal flat line. And then slope at this point is going to be my maximum negative slope. And then, of course, I'm back to my 0 slope, and so on. What we're going to want to do is keep track of these points, and I'm going to just draw some vertical lines so that we can, as we go down our derivatives, we can go from displacement to velocity to acceleration. So there's our different bits of the graph. It shows you how bad I am at drawing graphs, but these should obviously be evenly spaced out. Just to comment on axes, obviously we've got maximum positive displacement, maximum negative displacement, and then everything in between. On our x-axis, this is time. But we have a couple of different versions of time. Let's go ahead and put that in. Time is fine to describe it, but we could also talk about it as omega t, because time will be proportional to the change in the angle. And then let's just think about what this means at this point here. This dot here represents half of the circle. In other words, half the wave, half the motion, half the periodic motion. So this is going to be, let's just put this in above here. Hopefully you can see, this is going to be t half, right? Half the period. And that is equal to, I'm going to put this, let's put this in brackets. Above that, that is going to be equal to pi, right? Half a circle. So these are all totally interchangeable x-axis values. And then, of course, at this point here, at the end of the motion, this is going to be equal to 1 period, so t, or, as we've seen already, 2 pi, if we're thinking about that circumference of the circle. Those are totally interchangeable, so just put that in there. Okay, and then just in terms of a statement, we're going to start ourselves off here with the displacement value can be determined if we know the maximum displacement, x naught, and then that's going to be a sine of omega t. Now, like I said before, these are totally interchangeable. I have arbitrarily decided to start with a 0. So let's look at the derivative of this displacement graph. Of course, from kinematics and mechanics, you know that the derivative of a displacement time graph is going to be a velocity time graph. So let's go ahead and assume that this is going to be the derivative. And we can say that this derivative is going to be the change in x over the change in time. Now let's look at the graph. So we'll have a look at this 0 point. So this 0 point, we put this nice thick black line on here representing the largest positive slope. So hopefully you can see that that means this largest positive slope means that we're going to be starting at the largest possible positive value on our VT graph. So this is going to be my maximum, so that's my v naught, my maximum positive acceleration, and then the bottom of my y-axis is negative v naught, the maximum negative acceleration. Okay, so let's keep going. At this point here, this is a horizontal flat slope line on this dotted line, which means we have a 0 slope, so that's going to come to a 0 value here. And if we keep going, at this point here, we have our maximum slope, but in the negative direction. So that's going to be my V naught negative. And we keep going. I get my positive, my 0, and then my positive again here. So if I was to plot this graph out, it's going to do this, go down here, and up again. Okay, so what does that look like from a calculus perspective? Well, what we're doing here is taking the derivative with respect to x. Well, x is this formula here, so I can basically just plug this in. X naught sine omega t, and that's all going to be over with respect to t. Now here's where the calculus magic happens, and not to get hung up on it too much, but there's essentially a chain rule going on in here. So if we differentiate the x naught sine, that would effectively count as our outer differentiation, and then the omega t would be our inner. So I could probably just, maybe to help you see that, maybe put some brackets around the omega t. And that means we have this, I'll just flag it here, this is my inner. And then this whole thing here would be the outer differentiation. And that's where we're going to get our chain rule occurring. So I can then restate this as the velocity being equal to x naught, and the derivative of sine is, of course, cosine. So that's going to be in there. I'm going to leave a little space because I've got something extra to add in a second. So the derivative of sine is the cosine. Now I have to, and that's with regards to omega t still. But then if you do the derivative of omega t, you just get omega, and that's going to come in. I'm going to put that up front here. So I get my equation here, v x naught omega cosine omega t. Now, to simplify that even further, x naught omega is actually my maximum velocity. So I can say that v naught cosine omega t is what I'm interested in. And that's got us to a couple of these equations on our data sheet. Hopefully you can see my equation at the top here. This x equals x naught sine omega t, that is right here. And again, arbitrary whether I use sine or cosine. And then the one that we just did, this velocity x naught omega cosine omega t, or v naught cosine omega t, that is our equation right in here. And again, arbitrary whether we use cosine or sine. Okay, before we go on and look at our acceleration graphs, just one more thing to think about. I've just made a little bit of space here. It's often useful to think about maximum values here. So if I think about the maximum value for cosine, it has to be 1. So the max value that we're getting out of our cosine function has to be 1. And that corresponds to when the maximum velocities are at 1. So we can say that when the maximum value of cosine is 1, it's at its maximum velocity, positive or negative. So we can say, therefore, if we're looking at our velocity and we're trying to find the maximum velocity, we're going to be putting 1 into our cosine function. So I can say that my maximum velocity is going to be equal to x naught omega, and then the function of cosine 1, which is going to just cancel out. So I'm going to get x naught omega. So my maximum velocity is going to be equal to my maximum displacement multiplied by omega. That's useful to keep in our minds, and we're going to do this again when we look at our acceleration graph. So let's look at our acceleration graph. We want to think about these slopes. So qualitatively, the slope at this 0 time point on our velocity graph is going to be 0. So that's going to be translated underneath. The slope at my first intersection here, well, this is going to be the maximum negative slope. This is going to be a 0 slope, and this is going to be my maximum positive slope, and again, my 0 slope. So let's cascade that down. Let's first of all think about what values I'm putting in here. This is going to be my maximum acceleration, and this is going to be my maximum negative acceleration. Well, I'm starting with 0 slope, so I'm getting a 0 acceleration at this first point. Then I have maximum negative slope, so I'm down here, then 0, then maximum positive, then 0 again. So here we have a nice little graph, starting to look very similar to my top graph, except it's the opposite way around, it's inverted. So this would be my negative sine graph. That's going to play out in the calculus here when we do our differentiations of our velocity. So let's go ahead and do it. What are we looking at? Well, we're trying to get our acceleration, which is the calculus of velocity and time, or velocity with respect to time. So I'm going to have my differentiation of my velocity, which is either of these two, whichever I choose to use. Let's go ahead and put in my x naught omega cosine, and then I'll put it in brackets there, omega t. all with respect to time. And once again, we have our inner and outer calculus chain. Well, this whole thing would be the outer function. This would be the inner, so we have to treat them separately and use our chain rule, which we don't want to go into now, but you feel free to follow up on that if you want to. Otherwise, accept the magic of calculus. And we're going to say that the acceleration here is going to be, well, the derivative of cosine, which is negative sine. So I'm going to put my negative sign there, my negative symbol there, and then sine is going to go there just because I want to make my equation nice and neat. Then I've got x naught and omega, which can come in here, x naught and omega. Now, I also have the function omega t, which has to go through differentiation as well, which ends up being omega again. So this gives me a little square sign over my omega. So the acceleration is negative x naught omega squared sine omega t. Or, since we know that x naught omega is v, which we said here, we can also just say that the acceleration is negative, let's go back, negative v naught omega sine omega t. That's possible, just a simplified version. Or we can go one step further and say that, well, v omega is my acceleration. So I can say that the acceleration at particular time is going to be equal to the maximum, so the a naught, the acceleration naught, sine omega t. And now, once again, we're going to go ahead and assume that we can think of these max-min values for our sine value. So our sine value has to have a maximum, it has a maximum value of 1. So we'll do the same thing as we did before. Our maximum value has to be, for a sine, has to be 1. Again, remember that that is now corresponding to this maximum value here and this maximum value down here. In other words, when sine is 1, it's at its maximum acceleration, either positive or negative. So we can then say that our maximum acceleration is this v naught omega, and then this value of 1, which is going to come about from our maximum value of sine, which means we can just simplify this down to v naught omega, or our maximum acceleration x naught omega squared. Okay, so now we're getting close to the equation that's on our data sheet. Just one more thing for you to think about, and that's the sine. So let's think about the direction. Let's put a little asterisk here or an arrow here. At this point, this is our maximum acceleration, maximum negative acceleration. What is the direction of the acceleration with respect? What is the maximum direction of the maximum acceleration with respect to the maximum displacement? Well, take a look. They're completely opposite, right? Here's our maximum displacement. This is a positive value, and this is a negative value. And what this means is that we have to say, at this point, I'm just going to put this in brackets here, we have to say that the direction, and let's say the acceleration max, that's equivalent to the negative displacement max, right? Just look at the graphs. Equally, the negative acceleration max is going to be equal to the positive displacement max. Okay, so lots to think about so far. We're nearly there. Last bit to do is just to get to a point where we can understand a little bit about where these equations come from. We've already talked about these two. We've highlighted these as part of our thinking. The last one I want to get to then is this acceleration one. It's a bit different. So here's what we're going to do. Nice and easy. Using what we've just done, we're going to compare two things. We're going to compare the x value, which we derived, which is going to be x naught sine omega t. We should be okay with that. And we're then going to also look at this acceleration, which we also just arrived, which is negative x naught omega squared sine theta omega t. So what are we going to do? Well, hopefully you can see these two equations have a common factor. What is it? Well, maybe you can see I've got both of these equations have a sine omega t. So sine omega t is a common factor, but also if we take the x naughts, we can say that the common factor is x naught sine omega t. We can simplify and combine these two equations together. What do we get? We get a, acceleration, is equal to negative omega squared x. Okay, and that's what we do. That's how we get to this equation here. Okay, so hopefully that was worthwhile. Lots of detail in there, lots of complexity, lots of calculus. Again, it's important to know where they came from. They're not just magically appearing out of a magic box, but now you can say that you sort of understand where these three equations have come from. So now that we've seen where all these equations come from, our task now is to just have a look at some example questions. So here we have three. First of all, an object performing simple harmonic motion with a period of 0.40 seconds and an amplitude of 0.20 meters. The displacement is 0 at time 0. So what I'd like to do is just draw this out so we can visualize it as a sine wave graph, and then put all the values down and see what we can get from it. So there we go, we've drawn a nice little graph putting in the values. This would be a full period, which is our 0.4 seconds, which means this middle part must be 0.2 seconds, and we are told that the amplitude is 0.2, so the x naught maximum value must be 0.2 meters up here, and negative 0.2 meters down here. Okay, what's question one? Well, it asks for the maximum velocity. So here's our data sheet, and you might be tempted to look and see if you can find a formula for the maximum velocity, and you won't find one in there. However, we did just say that for a maximum velocity, which if we were to differentiate this down, we would find that the maximum velocity is when the slopes are the steepest. So, because this is a dt graph, so it would be here and here. That would be the peak of our velocity time graphs. And at that point, because we're dealing with sine and cosine graphs, that would mean that the maximum value of that sine cosine graph must be a 1. So hopefully you can remember when you're trying to find a v, the v naught, always think about that value of sine or cosine being equal to 1. That's the maximum value it can be. So we'd previously looked at that on our derivation, and what I can then say is my v naught is going to be equal to, well, we can use these equations, but we can just simplify it. It's nice and easy because cosine and sine, the value of that must be 1. So in other words, we can just simply say x naught omega. And that's because the cosine function has been basically cancelled out because it has to be equal to 1 for the v naught to exist. So now it's nice and easy. We're going to plug our values in. What do we have? Well, our x naught, well, we can figure that out in a second. Now we just have to think about omega. Well, omega is our angular frequency. And since we're dealing with a full circle, let's go ahead and say 2 pi. And then the period would be for this full cycle to happen. So again, just thinking back to our full cycle here, which relates to a circle. This full cycle would be equal to 2 pi radians of that. And that's then equal to the period, which is 0.4. So we can just go ahead now and plug in these values. my x naught must be the maximum displacement which was given in the question, 0.2 meters. And then I just have 2 pi. Okay, and then all over the period, which has to be 0.40 seconds. And that's going to give me, if I plug that into my calculator, 3.141 meters per second. And I'm going to, oops, there we go. I'm going to want to make sure I've got the right sig figs on this one. So I've got two sig figs in my values in the question. So my answer has to match that. So I'm going to say 3.1 meters per second. Okay, so question B, the magnitude of the velocity after 0.1 seconds. Okay, well, again, it's worth looking at our graph that we drew initially. So this is the, we've got the period, we've got the amplitudes, and we're asked the velocity at 0.1. So that's going to be the velocity about here. Now, if we think about what that means, the line here, or the slope, sorry, is horizontal, it's flat. So I'm thinking, just by looking at this qualitatively, I'm already thinking to myself, maybe the velocity at this point, let's write it here, the velocity is maybe equal to 0, because the slope at this point, at the 0.1 time marker, which would be here, that's a horizontal slope. So maybe the velocity is 0, but that seems like a trick question. So let's just go ahead and see if we can also work this through with the algebra. Okay, velocity. We need to know the velocity, so we're going to be using these guys here. Let's go ahead and plug some numbers in. What do we have? Well, we have the x naught. We do have that. Omega we can work out because we have the period. And then cosine omega t. Well, we're going to have t because we're given the time here. So I think we can just plug this in. Let's go ahead and start adding some values. So we've got the velocity would be x naught, which is 0.2 seconds. That's coming from the question right here. Omega, well, omega is 2 pi over the period, so 2 pi, and the period is also given in the question, 0.4. And then cosine of, once again, omega, which is 2 pi over 0.4, multiplied by the time. Well, the time is, in time in question is 0.1, so 0.1. Okay, plug all that into your calculator, and what do you get? Drum roll, yes, indeed, you get 0. Okay, so we can prove it both ways. We can look at the graph, and we can solve it with algebra. This is, again, another example of why I think drawing out these graphs, visualizing it is really helpful. And then obviously we've understood where this has come from. It's come from these graphs, and we can prove it sort of both ways. All right, last question, question C. Now we're asked to find the maximum acceleration of the object. So once again, it's worth thinking about our derivatives from our displacement time graph to our velocity time graph to our acceleration time graph. Hopefully you can recall that, let's just think about this, the maximum slope of our dt graph is going to give us a maximum velocity peak, but then that maximum velocity peak is going to give us 0 on our acceleration peak. So in other words, the acceleration derivative of this particular wave is going to be a negative sine graph shape. Okay, so the maximum acceleration of the object is going to be matched to the graph on here. So whenever it's at its maximum displacement, it's also going to be experiencing its maximum acceleration. Okay, fine. We also then need to think about the formulas that we might want to use. And the only one we have available for us on our data sheet here is this guy. Now the question is, how do we get the maximum acceleration? Well, don't panic, because of course what we can hopefully realize by looking at our graph is that, like I just said, when the displacement is at its maximum, the acceleration must also be at its maximum. So what we can do is we can just say that if we need to know the acceleration, well, we know that it's negative omega squared x, but I'm going to say at x naught, that is when the acceleration is at its max. Or to be a little bit more specific, when it's at the positive x naught, it's going to have its maximum negative acceleration. And when it's at its negative x naught, it's going to be at the positive acceleration. In other words, all I can do here is just substitute a for a naught. My a naught is going to be equal to omega squared x naught. And in fact, the acceleration, the sign, the symbol negative is kind of irrelevant in this because we're just going to give ourselves an absolute acceleration value. So I'm just going to ignore that negative sign for now. Okay, let's plug it in. Hopefully pretty straightforward by this point. So my maximum acceleration is going to be, well, 2 pi over t all squared multiplied by my x naught, which is 0.2 meters. Okay, so my maximum acceleration, if you plug it all in, ends up being 49 and 2 significant figures, and that's meters per second squared.